Okay, so welcome back to another video. So in today's video we have an integral from 0 to infinity of x to the power phi divided by x plus 1 multiplied by the square root of x to the power 4 phi plus x to the power 4 dx, and where phi is known as the golden ratio. This is the second golden integral, quote golden, on this video, so you're gonna expect some pretty interesting results in the end, but also interesting the interesting methods that you'll be seeing the way when I show the work of this. So let's jump right in. I'm going to define our given integral, so I'll just call this I. I'll let this equal to the same thing. So let's see. Let me first just for just making things look neat, I'm just gonna write the denominator first. Okay, so we have x 4 phi plus x to the 4th, and then x to the power phi. And what I'll do is I'll factor out an x to the power 4th from our inside square root, but you can actually take that square root and we'll get that it's going to be x squared. So this means, let's see, so x plus 1 and then x squared, yeah, and then multiply with x to the power 4 times 4 phi, and then subtract that with 4. So simply because I factor out the x to the power 4 from over here, and then that's a plus 1. And let's see, so then the numerator will still remain the same, dx. And then I'll rewrite this so this way the x squared from the denominator is moved to the numerator. So that means we just use our rules of exponents, x plus 1 and then x to the power 4 phi, and then subtract that with 4. And well, also I can actually factor out the 4 from that exponent too, so that it's x to the power 4, and then factor that out, so it's 4 times phi minus 1, and then plus 1. And then we move that x squared to the top, so using the rules of exponents, so this will be x to the power phi, and then subtract that with 2 dx. And so what I'll do now is I'll use a little following fact used from our golden ratio property. So the fact is that phi is equal to its reciprocal 1 over phi, then plus 1. So we use that to manipulate some things. So this means I can actually just substitute our fact from here back into this integral. So we get the new substitution is 0 infinity. Okay. And let's see, that means, so it's a plus 1 here, so when I subtract 2, so that means this will be a minus 1, so that means this is x to the power 1 over phi, and then subtract that with 1. Now it's x plus 1, and then multiply with the square root of, so let's see, we replace the phi, and then let's see, subtract that with 2, so it's minus 1. And so then this pretty much means that we have just x to the power 4 divided by phi, and then plus 1 dx. Now from here is we're actually going to perform a u substitution. So this means I'm going to let u equals x to the power 1 divided by phi, and we're going to have to factor in some stuff for x or substitute some terms for x in terms of u. So that means what I'll do is I'll solve for x over here, so that means we'll get that x is equal to u to the power phi. Alright, so that'll be important later, but now let's actually take the differentiation of both sides. So we get du is equal to 1 divided by phi, and this is just simply because of the power rule, and then to the power 1 over phi, and then subtract that with 1 dx. And so doing some things further, I'll multiply the phi to both sides, so that way I have phi du is equal to x to the power 1 over phi, and then subtract 1 dx. Okay, now we have our pieces together, and now we can substitute some things. So now with the new substitution, okay, so before we go any further, let me actually plug in our new bounds. So when x is equal to 0, then that would have to mean u is equal to 0, And then when x is equal to infinity, then u is infinity as well. No bounds have changed in this situation, so that's good. So now with our new bounds, okay, so let's see, replace x. Let me just start with the denominator first before I move to the numerator. So x plus 1, so I'll replace that with u to the power 5 plus 1, u 5 plus 1, okay. And then next is the square root of, let's see, x to the power 1 over 5, so that means this one will have to be u to the power 4 and then plus 1. Okay, so that's good. And now all that's left is our numerator. So we set that x to the power 1 over 5 minus 1 dx is equal to phi du. So to just do the substitution, this will be phi and then du. So now next, we're gonna have to perform another substitution. Another u substitution, I'll call this in terms of t. So this means I'll let u equals 1 over t and then take the differentiation both sides. So du is equal to -1 divided by t squared dt. And now we can factor out some stuff here. So we have the new integral. So that means we have to change our bounds again. So let's see, when we have u is equal to infinity, then that would have to mean t is equal to 0. And when we have 0 for u, then that means t would have to be infinity. And then now substitute some things back. So let's see, we have phi, then multiply with, so it's -1 t squared. And then with the denominator, let me extend the height of the integral just a little bit down. And so we have, let's see, u phi, so that means I'll take the u phi here. So that means this will be 1 divided by t to the power phi, and then plus 1, okay? And then we take the, now it's multiplied by the square root of u to the 4, so that means this will be 1 over t to the power 4, then plus 1. But we can actually continue simplifying some things further. First off, notice that you have 0 as the upper bound and infinity as the lower bound, so we would have to switch the bounds, making that negative. But that also means that'll cancel the negative from over here. So this would have to mean that now the integral is positive. Yeah, let me make the integral sign a little bigger. So let's see, infinity, 0. Okay, now before I continue further, let's actually simplify some things. Okay, so what I'm gonna do is I'm gonna multiply and divide a t to the power phi. So simply because we have a 1 over t 5 in the denominator, so we can just we don't want any sort of fractions under the denominator. And not only that, since t squared goes into the denominator as well, I'm going to put that back inside of the square root. So that means t squared, so when you square that, so now the input of that square root is t4 multiplied by this and distribute it, so we get that it's 1, the square root of 1 plus t to the power 4. And so now when we do all that, we get phi multiplied by t to the power phi, and then we divide this by 1 plus t to the power phi, and then we multiply this by, like I said, it's 1 plus t to the power 4. Here's the trick we're gonna do. So I'm actually going to stick this for u. We stick a dummy variable u back here, so that means now this integral will be in terms of u. But I'm also going to add back, we're gonna add this with this integral here that was in terms of u. So now this means, let's see, so that means rewriting the, well, not rewriting, but yes, rewriting, because we're sticking a dummy variable and then we're adding this, the integrals together due to the fact that it's linear, due to the fact of linearity. So let's see, u to the power phi and then plus 1, then the square root of u to the power 4 plus 1 du. Then I add this with this integral, but then that integral will be in terms of u. Simply, like I said, we stick a dummy variable. So then this is phi, then times u to the power phi. Then I divide this, 1 plus u to the power phi. Then multiply this with the square root of 1 plus u to the power 4, then dt. And then the addition comes out very nice. Notice that the denominators are equal to each other, so all we need to do is just add those two sums together so that we get that this is phi plus phi times u to the power phi. Then divide this by let's see, u to the power 5. I'm just gonna stick with the denominator in here. Simply, it's commutative under here, so it's fine with under addition. Let's see, then plus 1, and then times the square root of u to the power 4 plus 1 du. And now simplify some things out. I can actually factor out a phi. So this means I have 0, phi. And it's also a good thing to note that because these two integrals equal the same, this is actually the same thing as 2 times I. Like I said, they are both equal to the same integral, but I'm using a dummy variable for u and then take the sum together so we get double its quantity of I. So that's why the justification works here. So hope that clears any questions. Now, like I said, I can factor out a phi from the numerator, so we have 1 and then plus u to the power phi. Okay, then let's see, divide this. So the same denominator, nothing has changed yet. Then square root of u to the power 4 plus 1 du. And so you'll notice that these two terms, they cancel each other out from the top and bottom. So now the integral we have left is phi, then divided by the square root of u to the power 4 plus 1 du. So now what we're going to do here is we're actually going to perform a u substitution. I know, so many u subs. Okay, so this time I'll let u equals the square root of tangent theta. Now when we differentiate both sides, I'll actually take the chain rule. So I'll rewrite tangent theta to the power 1/2. So when we differentiate this, I get 1/2 multiplied by tangent theta multiplied to the power negative 1/2, and then multiplied by the derivative of tangent theta, which is secant square theta. Okay, and so therefore I'm simplifying some things out. We get that this is just secant square theta and then divided by 2 times the square root of tangent theta. Just underline what we have. Okay, so now from here we're actually gonna perform the substitution. So I'll just reiterate what our given integral is. So we have that the integral from 0 to infinity of phi, and then divided by the square root of u to the power 4 plus 1 du. So now when we perform the substitution, I get, let's see, so when we plug in our new bounds, I plug 0 for u, so that means theta would have to be 0. But then when I plug infinity for u, then that means theta would have to be pi over 2. And so now we perform the necessary substitutions from here. So let's see, du, and that means this is supposed to be phi, and then multiplied by secant squared theta. And then we divide this by, okay, let's see, if I plug u tangent theta, so that will be 2 times the square root of tangent squared theta, and then plus 1, and then multiply this again with tangent theta. Okay, so now the next step is that simply we're given that so far we've shown that 2I is equal to this same integral that after we perform the substitution. So I'll just rewrite it again, secant squared theta, and then divided by 2 times square root of tangent theta square plus 1, then multiply with tangent theta, and then that's d theta. So I want to show for I by itself, so I'll divide 2 to both sides, and so we get that so far I is equal to. So the only thing that's changed is that it's going to be a 4 on the denominator. Okay, secant squared theta, and then this will be 4. And then I'm actually going to jump to the next step and say that we'll use the identity that tangent squared theta plus 1 is simply equal to secant square theta. And then now multiply this by tangent theta, the square root of tangent theta. And then if we continue simplifying some things out, we get that this is 0, phi over 2. We'll get that the square root of secant squared theta is secant theta, but then that cancels the secant theta from the denominator, and you're only left with 1 secant theta on the top. So this is phi times secant theta, and then divided by 4 times the square root of tangent theta, d theta. Now, what I'm going to do is I'm going to factor out the phi divided by 4, but I'm actually not going to stop there. What I'm going to do is I'm actually going to rewrite phi divided by 4 as 2 times phi, divided by 8. And you'll see why you'll see why this is important later in the next couple steps, but let's not worry about that just yet. Okay, so pi divided by 2, and so we're left with 1 divided by the square root of tangent theta d theta. Okay, so obviously it's not easy to evaluate this integral by itself, so how about instead let's actually manipulate the bottom a bit. Okay, so let's focus on 1 divided by tangent theta. Okay, so now from here what I can do is I'll actually multiply the top and bottom by the square root of tangent theta, and so we get that this is the square root of tangent theta. Also realize this is supposed to be secant theta over here, so let's see, this is secant theta. I forgot about that, sorry, apologies for that. And so what I'll do is this is supposed to be secant theta on the top, so secant theta, and so okay, so let's see, secant theta, then multiplied by tangent theta, then divided by tangent theta. Okay, so far so good. I'll rewrite secant theta as 1 over cosine theta, and then I'll multiply that with the square root of tangent theta divided by rewrite tangent theta as sine theta divided by cosine theta. And you'll see the cosines will cancel each other out, so we're left with the square root of tangent theta divided by sine theta. Next, what I'll do is I'll rewrite this as 1 divided by sine theta, and then multiplied by the square root. Rewrite tangent theta as sine theta divided by cosine theta. And then what that means is 1 over sine theta, I'm going to put that back inside of our square root argument, so that means inside this will become 1 divided by sine squared theta, and then when I do this I'll multiply let's see, so sine squared theta, and then or sine theta, and then divided by sine squared theta, and then divided by cosine theta. And so what this does is the sine theta will cancel out from the numerator, so we're left with 1 over cosine theta, then sine theta. Well, I should have wrote sine and then theta first, sine and then cosine first, but that's okay. And then rewriting this, we also get that this is actually just equal to 1 divided by, now we can actually use the properties of square roots to separate the two out as a product of square roots. So this is multiplied by sine, the square root of sine theta, multiplied by the square root of cosine theta. Okay, let me just underline this. Okay, and so with that, now we can actually rewrite this. So let's see, so far I have 2 to the power 5 divided by 8, and then that's multiplied with the integral from 0 to pi over 2 of 1 divided by square root of sine theta, then multiplied with the square root of cosine theta d theta. Okay, cool. And so there I can actually write this in terms of the exponents. So let me just move this arrow over here, I'm running out of space. So far, so then when we write this with exponents, so we have, let's see, 0 pi over 2. So then this is sine of negative 1/2 theta, and then multiply with cosine of negative 1/2 theta d theta. And now we're going to recall a little fact that we're going to be using. We're actually going to be using a little function that we used several times in this video, also known as the beta function. So the beta function is in its integral representation. This is the integral from 0, or specifically this is supposed to be 2 times the integral. So 2 times the integral from 0 to pi, let's see, of sine theta to the power 2x minus 1, and then cosine theta to the power 2y minus 1 d theta. I can actually also use this too. This will come in handy as well. The further expansion, where beta can be expressed in terms of gamma function, the following formula is gamma x multiplied by gamma y, and then divided by gamma of x plus y. We'll be using this formula to rewrite this integral in terms of gamma. So before we do that, so notice that 2 times the integral of this, it represents the beta, so that means I can just multiply phi divided by 8 to our gamma formula over here. So that's why I wrote it in terms, that's why I decided to write 2 phi divided by 8 when I factor out the phi divided by 4, simply because we're going to be using this formula to change some stuff. Before we do that, we want to find what our x and y values are from this integral here. So first, let's actually find that. So setting the exponent to the formula 2x minus 1, let's see, 2x minus 1 equals, what is it, negative 1/2? And then 2y minus 1 equals negative 1/2. So let's see, I add 1, and then do the same thing here, plus 1. Then 2y equals 1/2. Then 2x equals 1/2. Then that means x is equal to 1 over 4 and y is equal to 1 over 4. So here and then here. All right, so now we know what x and y are, so we can plug those back into our gamma function. Okay, so we're actually just about done. So converting this integral over here, so let me also draw this new arrow. So and putting this 2 over here, we get that, here, I'll just rewrite the same formula again, why not? So 2 phi divided by 8, and then integral 0 phi over 2. Let me also write it like this. So this is sine of, let me see, 2 times 1 over 4 minus 1 theta, and then times cosine of 2 times 1 over 4 minus 1 theta d theta is equal to phi over 8 multiplied by gamma of 1 over 4, and then multiplied by gamma of 1 over 4, and then divided by gamma of x plus y, 1 over 4 plus 1 over 4, that's 2 over 4, so it's gamma of 1/2. But special value for gamma of 1/2 is actually just equal to the square root of pi. So therefore we have come to the conclusion that the final answer is phi multiplied by gamma square of 1 over 4 divided by 8 multiplied by the square root of pi, like so. And we have the final answer in this black box, like so. All right, that's pretty cool if you ask me.